Hello everyone and welcome back. Now, in the past two lectures, even though they were about vastly different things, right? 2 lectures ago I was talking about numerically approximating solutions to a differential equation. In the previous lecture I was talking about how we prove that a unique solution exists and how we can find it via successive approximations. Even though these two things seem very, very different, they both had something very important in common. And that is they had this updating step. That is, we took knowledge from what we currently know, and we had an equation that allowed us to update and get new information. Then we could take that new information and we could update and get even newer information. And in the case of, say, Picard iteration in the previous lecture, that helped us to build a series solution to our differential equation. In the case of the Euler method, it helped us to approximate the solution of a differential equation further into the future. Now, what these have in common is that they are examples of what are called first-order difference equations. So a general first-order difference equation can be written like this. Now, I'm going to just write this where y is a scalar quantity. So it's just a real number, okay? So we're going to move away from the Picard iteration from the previous lecture where these things were functions. Just imagine I get a number, and then I use it, and I update, and I get a new number. N in this case is the number of iterations. So here, y sub n is your current iteration. Yn plus 1 is your next iteration. You can go from, you sort of move discretely through these things, and you can go ad infinitum. Now, we have a lot of the same nomenclature that we use for first order differential equations. In particular, I would call this thing linear if f depends linearly on yn. Otherwise, nonlinear. The same way that we talk about ordinary differential equations, a lot of that language changes over. The only difference here is that this is not a differential equation. There's no derivatives anywhere. It is what's called a difference equation. That is the stepping procedure that we have in here. Now, typically, just like an initial value problem, this thing will come with some initial condition. So I call it y naught. So that is the n equal to 0 case. It's equal to some alpha, right? So just some number. Doesn't matter what that is. The point is, this is the analog of an initial value problem. So the same thing that I have always written in the top left of this board while we've been going through this lecture series. Now, one important case is what's called an autonomous first order difference equation. Now, we've seen the word autonomous before. We saw this in the context of phase line diagrams. And we know that autonomous means it has no dependence on the independent variable. So in this case, an autonomous equation is exactly the same thing. The only difference here is that now the independent variable is your n value. It's discrete. It's taking on the natural numbers instead of your, say, t or x or whatever you wanted to use in the ordinary differential equation case where it takes on the real numbers. Right, so this is very much a hopping algorithm, an updating algorithm. So same idea though, we call this thing autonomous if it has no explicit n dependence. Similarly, so let's take a little note here. Typically, we have a short form of denoting successive approximations here. So I have y1, well, this is f of y0. But then this tells me that y2 is f of y1, which is equal to f of y0. So a double application of f, which, to denote that double application, we write it as f. Sometimes I'll say this accidentally, it's squared, but this means like the second composition of f with itself. And then similarly, you can sort of repeat this, and you can put a 3 up here, so you compose f with itself 3 times. So what I really want you to be careful with is the notation. This is usually what hangs people up the most when they're first introduced to these difference equations. This does not mean the third power of f. It means f of f of f. It is a composition of f with itself. And in general, this would be the nth iterate in y is a composition of f with itself n times evaluated at the initial condition. So I really, 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 really want you to be careful with that, because a lot of people make this mistake on their first go through with these things. Okay, so remember when I talked about autonomous equations, I focused a lot on equilibria. Those were the balancing points, right? If you go all the way back to the very, 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 very first lecture in this series, I introduced equilibria, so that's where you have this sort of balancing of forces. What does it mean to have an equilibrium for one of these difference equations? Well, actually, we already saw it, and we saw it in the Picard iteration. It's a fixed point. And that means in the case of Picard iteration, it's a function that when you put it in, you get it right back out. In this case, that's exactly what an equilibrium is here too. So sometimes we call it a fixed point. Sometimes we call it an equilibrium. Sometimes we call it a steady state. There are all kinds of different ways to write this. But it's some say y star such that if you put it into the equation, you get it right back out. Okay, so again, if people mess up the notation here, then the other thing that they mess up is what it means to be in equilibrium in this discrete formulation, these difference equations, and in the ordinary differential equation context, which are continuous in time. Ordinary differential equation, your equilibriums are where the right-hand side is equal to 0. Derivative's not moving. In this case, equilibrium, again, means you're not moving, but we don't have a derivative in here to quantify that. So the way we show that something's not moving is we say if you put it into f, you get it right back out. Just going back to where you started. Nothing is changing from hopping to hopping. Okay, so let's do a little bit of a deep dive for a second. Let's do a deep dive on linear autonomous equations. Okay, so let's just try and walk through this. I'm going to use AUT to denote autonomous. So it's going to be linear, and it's going to be autonomous. Equations. This is going to be of the form yn plus 1 is equal to rho yn. So it's autonomous. Rho is just some real number, right? Rho does not depend on n. So rho is a real number. Okay, so what happens here? Well, first of all, let's just write down the first few iterates. y1 is equal to rho y0, and y2 is equal to rho y1, which is the same as rho squared y0, right? And then y3 is equal to rho cubed y0, and so on and so forth, until you get to the nth iterate, which is just raising rho to the nth power and then multiplying it by your initial condition y0. Nothing fancy. Remember, rho is just a real number, so this notation really is exponentiation. This is where these notations get a little bit hairy, right? This is why people make these mistakes, right? We have to keep in mind what each component is. These are functions. And so these powers on the functions, they denote successive applications, whereas this is a real number, so this is successive multiplications. This is really similar to this here is very similar to the notation of sine inverse, right? It doesn't mean 1 over sine, and a lot of people make this mistake early on. Okay, that's exciting though. What happens? Right? We spend a lot of time in math talking about limits. What happens to these things as we do this ad infinitum? Well, let's take a look. if I just keep raising rho to the power of n over and over, what happens? So let's say, where does the limit of this yn go? Well, if I have a number between -1 and 1, so exclusively, so say a half, if I keep raising that to successive powers, it goes to 0, right? A half, square it becomes a quarter, cube it becomes an eighth, raise it to the 4th power becomes a 16th, 5th power a 32nd, and so on and so forth until you converge into 0, right? Again, this is one of the things that we learn very, very early in our real analysis class. In fact, I believe I do it in the 2nd lecture of my real analysis series. Okay, so that means that if rho is between -1 and 1, this thing's going to 0. So the limit will be 0 if rho is less than 1. Okay, what if rho is equal to 1? Well, if rho is equal to 1, every power is also equal to 1. And so I just get y0. Okay, now if rho is equal to -1, I get y0 minus y0, y0 minus y0, y0 minus y0. Again, a very famous counterexample that we use all the time in real analysis. 1 minus 1, 1 minus 1. This very famous sequence that we know the limit does not exist for this sequence. Similarly, if rho is larger than 1 in absolute value, this thing just blows up to infinity. So in all of the other cases, this does not exist. And that's for every other case. Okay, now what I want you to pay attention to is for this equation, there is only one equilibrium because the right-hand side is linear in y, and that equilibrium is 0. If I put 0 in, I get 0 out. Now look what this is saying. If rho is smaller than 1 in absolute value, I converge to the only equilibrium that I have. Otherwise, I diverge. I move very, very far away from it, right? If rho is bigger than 1, then these things get bigger and bigger and bigger, and I get pushed away. So that same idea of stability and instability that we had from autonomous ordinary differential equations that we spoke about on the phase line diagram, same thing carries over here. We can say that 0 is stable when rho is between -1 and 1. Otherwise, we would say it's unstable. Okay, let's keep walking through this. So the purpose of this is to build up a bit of an intuition. Let's look at, say, a non-autonomous equation. So let's say, what about, well, let's have a fun one. Yn plus 1 is equal to, let's do rho yn plus, let's say, some bn. Okay? So there's some little perturbation that's taking place at each step. So you do your usual yn multiplication, and then I give you a little bn that might kick you in a different direction. Okay, let's do this. y1, well, this is rho y0 plus b0. Nothing exciting. All I did was set n equal to 0. But that tells me that y2 is equal to rho y1 plus b1, which now, if I take my y1 right here, and I put it in, and I do a little bit of simplification, I get rho squared, and then y0 plus rho b0 plus b1. Okay, I'm not sure I'm seeing a pattern. Let's keep going. y2 plus b2. Again, here's my y2. Let's put it in. And in fact, I'm going to use this piece right here. Well, here I get the rho cubed y0 plus rho squared b0 plus rho b1 plus B2. So first thing I want you to notice here is that I'm getting this homogeneous equation, right? The part that doesn't have the Bn. There's the solution to that thing floating through at every single step. But then, because of this inhomogeneity, this B part, this Bn part, I get these weird little twists and turns that are being added at every single point. And in fact, they're also being multiplied by that factor rho. So I'm going to go ahead, and you can probably guess the pattern now. If you can't, do y4, go to y5, go to y6. Keep going until you recognize a pattern. And in fact, you can say that you get rho to the n y0. Again, that's the solution to the original sort of homogeneous part that didn't have the Bn on the end. Plus, now we've got a big sum. I'm going to use j equal to 0. This goes all the way up to n minus 1 of rho to the n minus 1 minus j times bj. You might want to write that sum in a different way. That's perfectly acceptable. Essentially, it's just capturing this. Rho squared b0, rho times b1, and then no rhos times b2. Same idea, right? As the exponent on rho goes up, the index on b goes down, and vice versa. That's all that's happening with this. Do not be intimidated by it. I know it's a little ugly, but there's nothing wrong with it. Now, in general, it's pretty hard to say much about this, right? I don't really want to deal with infinite sums too much. I'm not really sure what I can really say about this. So let me make my life a little simpler, right? Again, we're just sort of exploring here. We're out on a little expedition. We're asking ourselves, what can we find? Well, let's say, what if every Bn was exactly the same number? Okay, so every single time, I get exactly the same number here. So every Bn is equal to some B in R. Well, in this case, then my Yn gives me rho to the n, y0. Again, we already had that. Plus, now let's take a look. I get this becomes a B, this becomes a B, this becomes a B. So essentially, I get 1 plus rho squared plus dot, 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 all the way up to rho to the power of n minus 1 all times b. And that's just because I could factor out the b from all of these successive applications. So that leaves me with just 1 plus rho squared, and you could have higher and higher powers of rho depending on how far into the iterations you went here. Okay, can we do anything with this? I hope that you maybe remember a little bit about your work with summations in calculus. And in fact, we do have a closed form of this thing. So actually, this becomes rho to the n y0 plus, and in this case, now I get 1 minus rho to the power of n divided by 1 minus rho. And then this is times b. And this is so long, so if rho is not equal to 1. Right? And the reason I need it not equal to 1 is because I don't want to divide by 1 here, of course. Okay, so what happens now? Well, the first thing that I can do is I can rearrange. I've got rho to the n and I've got a rho to the n here. So therefore, y sub n, let's put all of the rho to the n's together because that's really what I cared about in terms of my long-term limit. So that was what I cared about with this homogeneous equation. Well, now I get y0 and then minus b over 1 minus rho, and then plus, maybe I'll put it right down here, b over 1 minus rho. Okay, so why is that interesting? Well, again, if rho is less than 1, this implies that yn is going to converge, right? Because the only part here that depends on n is this rho to the n times y0 minus b over 1 minus rho. This whole thing is going to disappear, leaving me with just b over 1 minus rho as n goes to infinity. Otherwise, if rho is bigger than 1, or if rho is bigger than 1 in absolute value, this piece starts blowing up and nothing interesting happens. I'm sort of reduced to this does not exist case again. So clearly, the interesting piece here is when rho is smaller than 1 in absolute value. Well then, also, remember we excluded the case rho equal to 1 down here, so let's go back to that. What happens if rho is equal to 1? Well, I get 1 plus 1 plus 1 plus 1s all the way up. So really, what this tells me is that yn is equal to y0, because I get rho to the power of 1 again. So y0 plus n times b. Well, let's take a look at that. This thing is going to go, it's going to diverge. So it's, let's use this. So diverges if b does not equal to 0. So bad things happen again. So basically we get exactly the same scenario right here. Remember, I said that you're going to converge if rho is smaller than 1 in absolute value. You're going to diverge if rho is bigger than 1 in absolute value. And in this case, we had an edge case where rho is equal to 1. You kept getting your initial condition back. Now we see that if rho is equal to 1, well, some terrible things happen, and it comes exactly from this inhomogeneity, right? We see that as long as that thing is present, so as long as b is not equal to 0, then this n is just multiplying and multiplying and multiplying in, right? That b doesn't have to be big. It could be 10 to the minus 16. It doesn't matter if n's going to infinity, as soon as I'm bigger than 10 to the minus 16, or sorry, 10 to the 16, then this thing is equal to 1. And we're going to start blowing up, right? We're going to keep multiplying in. This can be as big as we want, and we get divergence. So that's one thing to consider, right? These things behave slightly differently than, say, your ordinary differential equations, right? You have different criteria for when you're going to converge to 0 and when you're going to diverge. And again, this is just for linear equations. This is just the sort of basic theory for how these things behave for general linear systems. Now, if you were to write down your successive approximations that you created for Euler's method, that thing is nonlinear. Now, if it's nonlinear, things get even more complicated. So let's take a look with another example. Okay, so we spent a lot of time talking about linear equations, and that's for pretty good reason. Again, nonlinear equations are hard to solve. If you get nothing out of this class, I want you to remember one thing. Nonlinear equations are hard to solve. We do not have cookbook recipes to figure out solutions to nonlinear equations in the same way that we have solutions to linear equations, right? I just went through all kinds of examples here, and I found exact solutions to linear difference equations. Unfortunately, I can't do the same thing for saying, assume we have a general nonlinear difference equation. But here's what I'm going to do. I'm going to present to you one of the most famous nonlinear difference equations. And it's actually very, very similar to an ordinary differential equation we have seen many times in the course of this class, and we'll continue to see. And that is the logistic equation. So if you go back to the class that we spoke about phase line diagrams, we talked about this thing where I had a derivative on the left-hand side. I called it the logistic equation. I said it represents a biological population of species. Okay, so imagine, without doing anything, let's just turn it into a discrete equation. So in this case, I just replace the derivative with a yn plus 1 here. You know, how bad can things get, right? So remember from the phase line diagram, the only thing that happens here is everybody converges to 1, and the extinction state 0 is unstable. Unfortunately, the dynamics of this equation are very, very different and very complicated. And a big part of it comes from the fact that we have this discrete hopping, and so we can make huge movements from iterate to iterate, so say from y1 to y2, and y2 to y3, and so on. We can make huge, huge iterates without having to care about what happens in between. This is different than a differential equation where you sort of have this smooth flow from one point to the next. Okay, so the first thing I'm going to do, I'm going to find my equilibria. Okay, so in this case, I've got 2 equilibria. It might take a little bit more work because essentially what I've got is y star is equal to rho y star times 1 minus y star, right? So I've got a quadratic equation that I need to solve. You can rearrange this thing. You might want to use the quadratic formula. You can divide off the common factor of y. And this gives 2 equilibria, 0 and rho minus 1 over rho. Okay, so again we see the extinction state 0, but now that carrying capacity state is slightly different, right? It actually doesn't represent the carrying capacity in this case. The carrying capacity is still 1, but nonetheless we get a non-trivial equilibrium, fixed point, steady state, whatever you would like to refer to it as. Those are all perfectly acceptable, but it's given in terms of rho. Okay, so the question is, what happens, right? How do I understand behavior that is not equilibrium? Remember, from the phase line diagram, lecture, there's a lot more going on, and we can capture it with phase line diagrams. But the question is, what can we do here? Well, we could, for instance, analyze the stability of these things. So the question is, do solutions or iterates that start nearby, do they remain nearby? Well, I'm going to do this in the context of the nonlinear equation, or the non-trivial equilibrium here. So let's do a little perturbation around it. So let me imagine my iterates look like this. Here's my equilibrium point, plus a little push off of it, okay? So the idea here is that my Vn term is going to be very, very small. Okay, so that means that my Yn, my actual iterates of this thing, are going to be very, very close to my fixed point. And the question is, if I start very, very close, do I get pushed away or do I get pulled in? Does Vn go to infinity, or does it go to 0? Well, let's take a look. If I put this Yn into my difference equation, I will get a difference equation for Vn, right? So Vn plus 1, that just comes from putting Yn plus 1 is equal to rho minus 1 over rho plus Vn plus 1 into the left-hand side here. Putting things into the right-hand side is going to give me, it's going to give me 2 minus rho Vn, and then minus rho Vn squared. Okay, so what can we see here out of this thing? Well, the first thing is, if Vn is small, then Vn squared is even smaller. Remember, I just spoke about with the linear context, if I have 1/2, if I square it, for example, it becomes a quarter. If I have 1 over 10 and I square it, it becomes 1 over 100. If I have 1 over 1,000 and I square it, it becomes 1 over 100,000. So this thing is going to be even smaller. So I'm going to do a little bit of hand waving here, but let's take a look at this. This is really sort of all that matters. The linear part. The nonlinear part is so small, it's negligible, right? It's like certain physical forces when we derive physical equations. Sometimes we can leave out the drag or the friction when we describe things sort of macroscopically. The idea is very, very similar here, that this Vn squared term is small enough that we can forget about it for now, and we just want to look at this little linear equation. But what's beautiful about that linear equation? Well, we see that essentially it's exactly what we were looking at in the first half of this video. So we can find, so that if the absolute value of 2 minus rho is less than 1, this is the condition, right? This is my multiplier in front of my linear equation. So if I slap an absolute value around that, if it's smaller than 1, then we're going to have Vn going to 0 as n goes to infinity. Again, I'm doing a little bit of hand waving, but this is very much true. It can be proved mathematically. There's no issue here with what I'm doing. So what is this? Well, we can open this thing up. This is the same as saying 1 is less than rho, which is less than 3. Okay, so what does that mean? That means that if rho is between 1 and 3, your solutions that start close to this unstable equilibrium right here, or sorry, this non-trivial equilibrium, are going to fall into it. What happens if rho is smaller than 1? Well, there is an analog of phase line diagrams that works for these difference equations that gives you, again, much of the information without having to do a lot of the math. So let's take a look at them. These things are called Cobweb diagrams. Let's look at the case where rho is between 0 and 1. Okay? When rho is between 0 and 1, this thing is negative. So again, if I'm thinking about a biological population, just like the logistic equation, I'm just going to think about what happens between 0 and, for example, the carrying capacity 1. So let's take a look. So I can negate this. I'm not really interested in it right now. So what I'm going to do is I'm going to put y along the horizontal axis here. And I'm going to plot this right-hand side as a function of y. Okay, so that means that I'm going to over-exaggerate this a little bit. I get something that looks like this. So here's 1. You're wondering why I'm making it so small. I'll show you in a second. 0. Now, in order to draw a cobweb diagram, I need to also plot the line y equal to x. So in my case, that's going to be this line, y equal to x. And I should label this as well. This is my logistic function, rho y times 1 minus y. Okay? So now, how do I visualize iterates of this equation? Let's imagine this is my y0 right here. Okay, so then the question is, where is y1? Well, y1 is whatever the value of y0 is inside of the function. So y1 is right here. So I'm just going to mark it over here. This is y1. But if I want to keep iterating this, I need to get y1 onto the horizontal axis, right? And so how do I do that? Well, what I could do is I could trace this thing over to the line y equal to x and just follow it down. y1. But that gives me, right there, y2. And then I can do the same thing. I can sort of follow this down. And here's y2. And then that gives me the value of y3, and so on and so forth. But of course, this feels tedious, right? It feels like I'm doing a little bit more work than I actually want to do. How do I streamline this? Well, this is where the idea of a cobweb diagram comes from. I go up, or I go vertically to the function. I go horizontally to the curve or to the line y equal to x. I go vertically to the function. I go horizontally to the line y equal to x, vertically, horizontally, vertically, horizontally. And what you can see here is that I am tracing exactly the iterates. Those iterates are where I hit the curve. So I'm going to draw them really, really big here to just super emphasize everything. But also, I'm visualizing the long-term behavior of the orbit. So I get y0, and then y1, and y2, and y3, and y4. And what's happening? Well, I'm wedging myself in, and I am converging to the fixed point, or to the equilibrium, 0. That's what's happening. So you asked me, Jason, what happens when rho is less than 1, if I go out to the left of this interval? Well, in this case, I'm seeing that I am converging to the other equilibrium. And in fact, if you do the same thing here, you do this little linear expansion that I just did, you'll see that 0 is stable using the same criteria when rho is smaller than 1. Okay, so what about this case when rho is between 1 and 3? Well, let's draw this up. 0 is less than rho. 1 is less than rho. And actually, let's put it between 0 and 2 in this case. I'll show you why in a second. So we can go all the way over to 3 in a moment, but let's just go between 0 and 2 for now. Here, start that cobweb diagram in exactly the same way. Every single cobweb diagram begins by sketching the function and sketching the curve y equal to x. So here, again, I'm going to sort of over-exaggerate the function. It's just a sketch. We don't have to be too precise. And here, now the curve y equal to x intersects at 2 points. What is this point of intersection? Well, that is where the curve rho y, 1 minus y, is equal to y. Oh, it's the equilibria, right? So the intersection of these two curves is exactly the equilibria. We see it right here. We see it right here. And we see it right here at rho minus 1 over rho. Now, the reason I restrict myself to between 1 and 2 is because if you go from 2 to 3, you actually go over the maximum of this little hump function. And what happens is the dynamics will alternate in. So what this leading number is, it becomes negative, and you go from plus to minus. So let's just look at this for a second. Let's imagine I start with my y0 here. Cobweb diagram, nice and easy, right? It's almost as easy as a phase line. Vertical, up. There's my y1 value. Horizontal, over. Vertical, up. There's my y2 value. Horizontal, vertical. And now, I mean, I drew my picture so sort of exaggerated that it's very hard for me to squeeze much more in. But what you can see is you can visualize the stability, right? Now you're getting very, very, very close to that equilibrium, and you're actually converging in. Now, if I fix this picture just a little bit, just to sort of exaggerate it so we can see it a little better, let's imagine it looks like that. I apologize, it's not the prettiest picture, but you can do the same thing from the other side, and you would go, say, up, over, and then you fall into the same thing, right? And let's just do one more. Let's get a little closer here. You go up, over, and now you're converging in from the top. All right, so I didn't draw the prettiest pictures for you, but you can see what's going on, right? And you can keep going with this. So I want you to sit down, just grab a little notebook right beside you, and sketch out that function for different values of rho, and draw some cobweb diagrams. Have a little bit of fun with this. But the question that I want to pose to you is, I figured out what happens if you go below here. What happens if you go above here? Because 0 is not stable, and this non-trivial equilibrium value, rho minus 1 over rho, is also not stable. What's going to happen? Well, something that we don't see in ordinary differential equations. So for rho greater than 3, you can actually prove this. We're not going to go into this in detail. This is more left for a dynamical systems class. And what you can find, so first, 0 and rho minus 1 over rho are unstable. That is, if you start close to them, you will be pushed away, just like 0 was unstable with the logistic ordinary differential equation. In fact, what you get is a 2-cycle becomes stable. So what's that? So a 2-cycle becomes stable. And in this case, you get these 2 points, y plus or minus, which is equal to 1 over 2 rho, and then times rho plus 1. The actual values of this don't really matter too much. Rho minus 3, rho plus 1. But it's important for me to really explain what it is that I just said here. What is a 2-cycle? Well, a fixed point is a value that you put in and you get it right back out. So what's a 2-cycle? You put in, say, y plus, and you get y minus. You put in y minus, and you get y plus. You put in y plus, and you get y minus. You put in y minus, you get y plus. So what do you get? You're hopping between 2 values in your iteration. Right? It's not a fixed point. A fixed point, you get the same thing in as you get out. So you get a constant sequence if you start at the fixed point. A 2-cycle, you alternate between 2 values. I go from y plus to y minus, y plus to y minus. And so what you can actually find here is that this thing is stable for 3 less than rho less than 1 plus the square root of 6. Okay, so that again gives a finite region, right? So you're asking yourself, well, Jason, I'm an inquisitive person. I want to know what happens if I keep going. If I go above 1 plus the square root of 6, what happens? Well, what happens is that the cycle that becomes stable, the one that gets birthed, is actually, it has a double period. It's actually a 4-cycle. So you go from one value to the next, to the next, to the next, back to the first. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And that thing is only stable for a little bit of rho until it doubles again. And then you get an 8-cycle. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then the 8-cycle destabilizes. You get a 16. Then you get a 32. Then you get a 64. Then you get 128. Then you get 512. All the way up. And actually you can show for a finite value of rho that you actually can do all of these doublings until you sort of reach infinity. And that's what we call chaos. This is the sort of prototypical example of modern chaos theory. Right? The original exploration of this goes all the way back to Robert May, I think in the 50s, where this was first observed. This is what sort of led people to be very, very curious about the massive discrepancies between ordinary differential equations, where you have this sort of continuous flow from one state to the next, and these discrete difference equations where you can sort of hop around and you get these extremely complicated phenomena which eventually can potentially become chaotic.